as a projectile motion problem. As I said at the beginning, and this is the simplest one there are, in AP Physics 1, I break these up into types of problems. And if I was doing the same thing here, I'd call this a type 1 problem because it's just stupid simple. Any one of the types of problems I would throw out here, I'm throwing them out there because I could refer to it as a type 1 problem. You would never open a textbook and see anything about type 1 projectile problems, okay? I'm just making that up. But in this problem, I get to insert a 0 because anytime I can insert a 0, it tends to make our problems easier. But the first thing I want to point out in any of these problems is that we are taking a two-dimensional problem and breaking it up into two one-dimensional problems. Now, part of the reason we do this, and we will do this all year long, we will always break our problems up into one-dimensional problems because you don't have two- or three-dimensional math. We have one-dimensional math. All the mathematics you've ever learned, no matter the most complicated calculus, is still only one dimension at a time. So our mathematics doesn't support working in two dimensions at once. They can be tied together, but our mathematics doesn't support it. There are forms of math that do handle 2 and 3 dimensions at once. We just don't teach those in high school. So when we consider what's happening here, we're going to have a vertical direction and a horizontal direction. And like everything else in here, I attempt to create a framework for you to organize your information. The vertical direction is going to experience uniform accelerated motion, right? It will have a constant acceleration. The horizontal direction will have no acceleration, which means in the horizontal direction, I have just a horizontal velocity, a time of flight, and a change in horizontal position, which we call, by the way, the range of your projectile. In the vertical direction, I will have all the same kinds of motion variables, but I want to associate them with the y direction. So I'll say things like delta y instead of delta x to differentiate the two displacements. I'll have v, y, naught, indicating whatever the initial vertical velocity is. I'll have vy, suggesting the final vertical velocity, acceleration, and then time of flight. Basic projectile problems are problems generally where you're being asked to figure out one of these sets of variables. How fast would I have to roll the ball to land at the target? How tall is the building if it lands this far away from the edge? It's something like this. The most common question to ask is, what is the range of the projectile? Where on the ground does it strike? But these problems have one thing in common. The time it takes to go vertically is equal to the time it takes to go horizontally. That ties the two sides of the problem together. But the two sides of the problem are independent. How fast it's going horizontally doesn't affect how fast it's going vertically. So in a problem like this, if I wanted to figure out, say, where it strikes the ground, all I have to do is try to understand what variables I've been given and see if I can find the time on one side and plug it into the other. That's a basic projectile problem. So here we go. Put my equal signs on everything. And before I get started, something that you guys had a problem with on the last test, more in fifth than this, I need to identify what direction I will be using as positive in both cases. I'm going to use upwards in the y direction to be positive and to the right in the x direction to be positive. Look, I don't want to harp on this, and I want to be incredibly clear and precise. This, still not physics, but the next unit is forces, and forces, we finally start getting into physics. I spend an incredible amount of time saying out loud, you have to choose what direction is positive. That becomes exceptionally important in our next unit. So please don't minimize this step. I know I talk a lot, but I'm talking a lot in trying to give you time to emphasize this in your notes. That make this a big part of all problem solving, and you will be much better for it. All right, so delta y looks to be 3 meters, right? It falls downwards 3 meters. At the same time, it has an initial y velocity of 0. Because it was just traveling horizontally, it has no vertical velocity. At the same time, it's being pulled downwards by gravity, 10 meters per second squared, and has a horizontal velocity of 2 meters per second. Applying the direction as stated in the problem means my 3 meters is negative and my 10 meters per second squared is negative. So like any of these kind of basic motion problems, we spend our first few minutes identifying the information that we have been giving and try and organize it. Now, look guys, this means these problems can have multiple velocities and multiple displacements. No longer do I just find the thing that has meters and put it in displacement. There's 2 possible displacements. You guys seeing that? Use a structure. It will help you organize your information. It'll also help you search out what information has been given. But clearly, I'll need either 3 pieces of information on this side to solve for the time, or 2 pieces of information on this side to solve for the time. Either way, if I want the range, I'm going to need the time. Now, the left side are our standard motion variables, so all the Galilean motion equations apply. The right side, there's no acceleration, so it's just delta x equals vx times t. The result of the Galilean equations if there's no acceleration. Can you figure out where it lands on the ground? Do you need me to work this problem out? Give it a shot. We should all get the same answer. I just kind of wanted to see if people would start the problem and kind of know what I was expecting. Those of you who jumped right in and knew what to do, good job. Thank you very much. Those of you who didn't know what to do, phooey on you. You should be paying better attention. I want the time. I don't need the final velocity. This points to a particular motion equation that could be used to find the time. Probably something like delta y equals 1/2 at squared plus vy naught times t. Putting the subscripts in the y direction does not change the inherent message of the problem. So I think we can do a pretty good job translating this into the y direction and be okay with it. That's going to be -3 equals 1/2 times -10 t squared plus 0. So this is going to be the root of 0.6, I think, which has got to be somewhere around 0.8. What is it? 0.77. Now that's how long it's in the air. Not very. But that's how long it takes to fall. It's also how long it takes to go sideways. Right? That's all it is. You find the time on one side, you use it on both. Which means my range, where it strikes the ground, is going to be 2 meters per second times 0.77. So 1.54 meters. Don't forget our units. All right? Not terrible? Let's see. Now that we've done one, I know you'd love them all to be the same, but not so much. I mean, we didn't talk about trig last week just for funsies, right? So I kick a ball from the ground. It's going to land back on the ground. I would call this a type 2 problem. Again, I make up these types. But can you see the difference in this problem and why it's specifically different than the other one? But there's a 0 in this problem. There's something about this problem that's going to introduce a 0 by doing it this way. I want you to think about what's going to happen to the projectile. It's going to travel upwards and then strike the ground, correct? What's the vertical displacement of the object? 0. The vertical displacement would be 0. So when I start considering my chart here, with delta y, vy naught, vy, a, and t, and delta x, vx, and t, the first thing I can introduce is that delta y is going to be 0 on the vertical. Again, obviously, each one of these is kind of a specialized version of a projectile, and you can kind of imagine that the final version of this is one that's launched at an angle off of some height. Adding a 0 just simplifies the math. However, I am introducing something here. Do you see what I'm introducing? What we have is the actual vector of launch, but we can't work in 2 dimensions at once, which means we have to take this vector and break it up into component vectors. Component is a vocabulary word, and components are 2 vectors that represent another vector. Components have rules. Component vectors have to be in different dimensions. So in this case, we've aligned the x direction with the horizontal and the y direction with the vertical. So these 2 vectors are components. One is totally in the horizontal direction and one is totally in the vertical direction, but they can be used to define the 2 meters per second at 30 degrees. Hopefully you see that one of these is going to be the Vx velocity, while the other one is going to be Vy naught. Do you guys see that? One's going to represent the initial vertical velocity. That one's acted on by gravity. The other one's going to represent the horizontal velocity, which doesn't change. But you were taught really quickly how to do trig, right? So you can figure out what those 2 should be. I'm going to talk out loud while you guys get me numbers, but I'm going to end with something that's not numbers. You're going to end with something that is numbers, okay? So you find the values. But I'm going to say a few things out loud about what we talked about when it comes to solving triangles. We did talk about that last week, right? So I'm going to identify an angle of focus. That's my 30 degrees. I'm going to label my triangle sides: opposite, adjacent, and hypotenuse. I'm going to write out some trig functions to correspond with that 30 degrees. Sine theta equals opposite over hypotenuse. Cosine theta equals adjacent over hypotenuse. And tangent theta equals opposite over adjacent. I'm going to note that the opposite side is actually Vy naught. And the adjacent side is actually Vx. And the hypotenuse is whatever the launch velocity is, which I will dub V naught. And I'll point out that Vy naught is always going to be the launch velocity times the sine of the angle, and that Vx is always going to be the launch velocity times the cosine of the angle. And I'm going to propose to you that if your trig is poor, that you could memorize that. But you'll still need to be good at trig, because we're going to do other triggy things. But I am just going to write in here V naught sine theta and V naught cosine theta. As a means of driving home, you could memorize that for now. But in this problem, the launch velocity in the y direction is 1 meter per second, and the launch velocity in the horizontal direction is 0.866 times 2, or 1.7 meters per second. So I have an acceleration of 10 meters per second squared. And I'll make upwards positive and to the right positive. Now again, I have a 0 in here. That kind of helps, but my goal is still the same. Find the time on one side, plug it into the other. So delta y equals 1/2 a t squared plus vy times t. Since delta y is 0, I can solve this through factoring. I can have t and negative 5t plus 1 equals 0. So t equals 0, or t equals 0.2 seconds. Any question where I got any of those?
Yeah.
Which one?
I don't see how you got the 1.7.
You have a calculator? All right, so based on my triangle, Vy naught is going to be V naught 2 times the sine of 30 degrees. I bet your calculator isn't in degrees. Just throwing it out there as a possibility. In any of ours, if you get a negative for the result of sine, your calculator is not in degrees, because we're always going to be dealing with angles that are between 0 and 90. So we will always get positive values for our trig functions. How are we doing? Did that fix us up? It's also a 30, 60, 90, and the sine of 30 is half. The cosine of 30 is square root of 3 over 2, right? I'm patient, though. No pressures, I just stare at you. You sure? All right. All right. So, are we doing okay?
Yeah.
There's not a whole lot of meat here. It's all the same stuff. So I tend to not want to spend a lot of time on it. My time is 0.2 seconds. So if I want to find out where on the ground it lands, it's 1.7 times 0.2, which appears to be 0.34 meters away. I don't have to use the t equals 0 because that's where it was on the ground at first. Now, you kind of know what's coming next, don't you? I mean, can you kind of see where I would go? If not, then I'll make it clear. The only kind of problem we haven't really talked about might be what would happen if I go back to that shed, which is 3 meters off the ground, take the ball, which again, 2 meters per second, but launch it at 30 degrees from the top of the building. Give this a try tonight. It's all the same stuff you just did on type 1 and type 2. It's just a type 3 problem. It's still just algebra. It's nothing special. We'll talk about weird stuff tomorrow.